of our means-based tests to set up what we're going to be doing with repeated measures and ANOVA. Again, I really like these designs just because they're intensely powerful. Much better equipped to tease out some of the types of effects we're probably interested in taking a look at. I'll give you a couple of different examples of what that's looked like in some of our research that we've done through our lab. So finished up with our paired sample t-tests, right? The idea is, again, remember that paired sample t is just a one sample t-test on a vector of different scores, right? We have here scores at time 1, scores at time 2, but at the end of the day, score at time 1, score at time 2 isn't actually relevant to anything, right? Only thing that we're getting from time 1 and time 2 is this vector of different scores. So remember, when we're screening paired sample data, this set of different scores is actually what we're wanting to take a look at to test normality in the distribution of sample means and sort of some of that type of stuff, right? So once we go through and we calculate that different scores, this is the primary output. And our test is the mean of the different scores minus our expected value under the null, which is 0, over the standard error of the mean of the different scores. Get our standard error here as standard deviation of the different scores over the square root of n, right? This is just a formula for a one sample t-test. That's all that is. We're just using the mean of the different scores and the standard deviation of the different scores as the inputs for that, right? And so this ends up being a powerful test, again, because what we're doing is we're getting rid of all that individual different stuff and just looking at variability in the different scores here. Okay. So transitioning this over into our repeated measures ANOVA designs. If we're thinking about our between subjects ANOVA, right? We're saying that across treatments 1, treatment 2, treatment 3, and mainly you're running a study where you've got 3 different conditions that you randomize people to go through. We're assuming that individual scores across treatments 1, 2, and 3 are all independent of one another. The correlations between these treatments is 0 because they're randomly assigned to completely different things. Random person A in condition 1 and random person, the first person in condition A and the first person in condition B, their scores should be completely uncorrelated because they're different people, everything's independent, right? So again, because we have different people completing different treatments, expected value correlation in this set of scores is going to be 0, right? But instead of us having treatment 1, treatment 2, treatment 3, where I've got, say, 20 people in treatment 1, 20 people in treatment 2, 20 people in treatment 3, let's say instead that instead of a sample of 60, we've just got one sample of 20, right? And there what we have is 20 people participate in the first condition, and then the same 20 people participate in the second condition, and the same 20 people participate in the third condition. We've got the same people for all 3 conditions. Now all of a sudden, correlation between scores is almost certainly not 0, right? Because I've got Layla participating in condition 1, condition 2, condition 3. If these scores are outcome on some, say, measure of subjective emotion, right, sort of pleasant to unpleasant, I'm going to expect there to be some level of correlation across those scores, okay? Oftentimes, this is a big, big problem with most of our analyses, right? Because we're expecting sort of scores here to be completely uncorrelated with, we talk about, if this happens and we don't mean it to, we've got a problem with independence assumptions, right? I'm assuming that in my between subject designs that Evelina scores are unrelated to Haley scores. And if they are, I've got dependence in there and that's a problem. But for our repeated measure designs, we know that these are going to be correlated. We expect them to be correlated, and what we can do then is we can go through and use the correlation between these measures to go through and start to capitalize on that and increase the power of our tests, okay? So again, this, condition 1, condition 2, condition 3, we're expecting all of these to be on correlation of these scores is 0, but as soon as we turn this into a repeated measures design, where now we have the same group of people participating in complete condition 1, condition 2, condition 3, we completely restructured how we go about this stuff, okay? we kind of get a headspace for sort of the situation here. We've introduced something that's generally a problem and a violation of our independence assumption, but we're going to utilize that to create a more powerful test. All right, so if we're taking a look at this table right here, so we've got treatment A, treatment B, and treatment C, okay? If I'm looking at scores in this table, I'm seeing a great deal of variability within treatments and a little bit of difference between treatments. Nick, can you tell me how I'm arriving at that? How did I arrive at that conclusion?
As you, in each treatment group, A, B, and C, there's high variability. The range goes from 30.
Yeah.
And then between the treatments, it seems as if they're going up in each treatment.
Okay.
So there's variability within each treatment itself and between the treatments.
Okay. And where am I getting to see more variability? Within or across treatments?
Within.
Within treatments, right? If I look at scores in treatment A, in treatment B, and treatment C, I'm seeing all sorts of, people are all over the map on this stuff, right? And if we're seeing high levels of variability within a treatment, what do we call that? Error, right? Because if I've modeled, if the only thing that impacts outcome is sort of whatever is involved in my treatment, then everybody in here should have about the same score, right? If I'm not getting that, and people within my condition have a wide variability in their scores, that's a problem because that's stuff that I haven't accounted for, right? And so in this table, we're seeing a huge degree of variability within cells and only a little bit of variability across the cells. And so what does this typically spell, Kate, in terms of our between subjects ANOVA designs?
Sorry, can you repeat that?
Yeah, so if I'm seeing a whole lot of variability within groups and not a lot of variability across groups, what does that suggest for my hypothesis test?
So there's a lot within.
Mm-hmm.
Then there's like some type of error that
Right.
you're not
What's what's the likelihood that I'm going to be able to reject the null hypotheses in this scenario?
lower?
Yeah, it's probably not great, right? If I've got a lot of error within my groups and not a lot of variability within my groups and not a lot of differences across my groups, that doesn't look good for my chances of sort of saying, oh, I've got something going on, okay? So again, if this was a table that we were going to analyze with our between subjects ANOVA, we've got high within group variability, so this is going to be error, little between group variability, which is our effect, and if we're taking a little effect to a lot of error, that's not a good situation, okay? But if we go through and we take a close look at this, Haley, what am I seeing kind of that looks like could be going on across these cells?
There's a larger increase from A to B.
Yeah,
to C.
and it's pretty systematic, right? Within each individual, the increase from A to B to C is looking about the same across each one of these cells, right? And so what it looks like, again, if we're assuming that this is not a between subjects design, but a within subjects design, all of a sudden we start to change our evaluation of these data, right? So we see for subject 1, we've got an increase of 2, 3, 2, 1. We've got a bigger jump here of 7, and then a jump up. We're seeing systematic increases across these treatments, even though the overall sort of level, the overall profile, people are coming in at very different levels, right? And so what we see here is that a lot of the variabilities is a function of individual differences, right? A lot of the variability that we're seeing within these data is just due to different people coming in at different levels, right? This is something that for clinical folks we might see if we're doing sort of a treatment outcome study, right? Different people are coming in with different levels of symptoms. That's not shocking. That's kind of what we would expect, right? Or, you know, if I'm looking at social psych and I'm looking at sort of personality types of stuff, right? I expect people to come in at different levels of some variable, right? I'm not expecting everybody to come in right in the middle or right at the same level. But if we look at the pattern of behavior across each one of these conditions, what we see is everybody's kind of doing the same thing as we're moving forward, even though people are coming in kind of at different levels at the start, and maintaining those across the study. Right? Same thing with, again, if you do work with physiological data, right? If I take someone's skin conductance, people are going to come in all over the board on skin conductance. But if I follow skin conductance over time, those measures are correlated 0.9 with one another or above, right? So we're seeing, even though sort of the amount of sweat that you have in your hand, sort of just the general stuff is going to vary widely across people. Within subjects, we see very little, very systematic change across this, right? And so what we do with our repeated measures designs, as opposed to this, right? When we go through and we have the same set of people that we're following over time, what it does is we reduce our overall error term in our ANOVA, right? Because what we do is we parcel out all these individual differences, right? We take all those individual differences and we suck that out and we say, okay, those individual differences are due to, they're just differences in where people are coming in. And so what ends up happening is we suck that out of our error term, resulting in less noise. We model that individual difference in a separate place. And what it ends up doing is it increases the power of our tests, because we have differences, but we know why those are different. Those are differences attributable to just people coming in and being at different levels when they come in. Just people are different, right? What we want to do is take that, pull that variance out that's creating some of that interdependence, and just look at systematically how people are changing across a set of assessments. So we've got less noise, and if we've got less noise, we end up with a bunch more powerful tests of whatever effects it is that we're looking at. Okay. People comfortable conceptually with what we're doing and how, from a mathematical, from a statistical standpoint, what we're kind of pulling out and separating out here? Cool. Okay. So for our one-way repeated measure ANOVA design, we've got one outcome that we're measuring on multiple occasions. Okay. So essentially, we have multiple dependent variables in this outcome, and so our hypothesis of interest, or our research question with our one-way repeated measures ANOVA design, we're asking, do scores vary across repeated assessments of whatever our outcome is? Right? Do we see, if I measure this again and again and again and again, do we see systematic changes or systematic variability across these repeated assessments? So my null hypothesis here is that repeated measure 1 equals repeated measure 2 equals repeated measure 3, so on and so forth. All right. So if we think about how we go through mathematically and partition this variability out, and again, think about this and don't gloss over this. I mean, oftentimes I see a summation and I immediately sort of drift off into somewhere else. Think about this, because it's going to start to become important in sort of understanding what these analyses are doing, and then also when we start getting into effect sizes for repeated measures designs, you're going to have a good understanding of what variability is going where and what it means and how we're sectioning everything out. Okay. So if this is our table that we're working with up here, we're going to start out with our sum of squares total. Sum of squares total is just all the variability in this set. Literally, if we want to go through and calculate this kind of conceptual formula here, this is going to be the sum of all of our squared deviation, squared deviation of each individual score from the grand mean, right? So if I'm calculating sum of squares total, it's literally taking score 2 minus 18.76 and squaring that, 10 minus 18.76 squared, 22 minus 18.76 squared. This is all the variability in the set. This is the total piece of the pie, right? This is all variability of every score in this entire set is getting captured by our sum of squares total. This is the variability that we have to work with. Okay? But then what I'm going to do, always, when we're thinking about repeated measure designs, first thing we're going to do is we're going to take that variability that's due to just individual differences across people, and we're going to suck that out, okay? And from a mathematical standpoint, how we're doing that is we're taking the mean of participation, or the mean of each individual subject or participant minus the grand mean and squaring that deviation score, summing those up, multiplying it by k. This is going to be the number of repeated assessments, right? So I've got, in this small set, I've got this person's average across the 3 assessments is 4.33, right? So I'm going to take, if I'm getting sum scores between, I'm going to take 4.33, subtract it from 18.76, I'm going to score that. And I'm going to take 11.67, that's person 2's average across the assessments, subtract and square that deviation score. For average for person 3, take the square of the deviation, 4, square the deviation. I'm going to sum all those scores up and then multiply it by 3, because that's the number of repeated assessments I've got. Okay. What this represents is the variability just to do to the individual differences across people, right? Now, what happens if I come in and everybody in my study has the exact same average across these across the 3 repeated assessment points? What's my sum scores between? What do you think, Lynn?
1. Well, no, because you have to multiply it by the number of assessments. So
Yeah,
3.
but if everybody has the exact same average, this is average of 10, 10, 10, and 10. What's my grand mean? What's the average of 4 scores of 10? 10, right? So if I subtract this from this, what do I get?
0.
0, right? And so what happens then after I take 0, multiply it by all this stuff, right? Cancels out, right? I literally have no variability between participants. Everybody is common and everybody is sort of responding the same way. This is never going to happen, right? But you can see in this extreme case, that would literally mean there are no individual differences across people. Everybody's coming in and responding the exact same. That would make your model crash. But you can start to see what we're grabbing and what we're capturing with this between subjects. And what we're doing is we're saying, okay, that's between subjects difference, that's individual difference stuff. We're taking this out, okay? As before, with the between subjects design, that would have gotten dropped into our error term. That's going to go in the denominator of everything that we capture. And if our denominator is massive, what does that do to our F-test? Shrinks it down, right? What we're doing is we're partitioning this out and saying, this isn't relevant to what we're really interested in. We're really interested in systematic variation of means across time. We're going to go through, suck out individual different stuff, accounting for the correlation between these things. And once we put that out, we're left with our sum of scores within subjects. Okay. Now we'll get sum of scores within by subtraction. This isn't something that you'll need to have it in terms of calculating effect size, but getting the sum of scores for your repeated measure, your sum of scores for your effect. This is going to be the sum of your the deviation scores of your repeated measures in your grand mean times the number of people that you have in your cells. Okay, so here for sum of scores repeated measure, we're going to take the mean of condition A. We're going to subtract it from the grand mean, square that. Mean of condition or of assessment B, subtract that from the grand mean, square that. Mean of scores on the 3rd time point, subtract it from that. Take the sum of those square deviation scores and then multiply it by, in this case, 4, because we've got 4 people, right? For a one-way, can we have an unbalanced design with a one-way repeated measures ANOVA? What's up?
If someone doesn't show up for all of the...
If someone doesn't show up, do they get included in this analysis? Nope, they're gone, right? So this is a little bit different for these the repeated measures ANOVA design. This is still like a basic OLS type of, but this isn't, we're not running a maximum likelihood thing where we're sort of using, where we are able to capitalize on everybody else. If you've got someone, a missing value, if someone doesn't show up for an assessment point, with this traditional approach, they're gone. You can't evaluate yourself. Okay. So because of that, can we have an unbalanced design with a one-way repeated measures design? Nope. So N is easy. It's just however many people you have in your sample, because that's who's going on. Anybody who is missing a score anywhere gets kicked out. It's sort of list-wise deletion, just like sort of all of our other stuff. Okay. So what this is going to give us, our sum of scores repeated measure, this is going to give us our effect that we're actually interested in looking at. And then our error is going to be the difference between our total minus our between minus your repeated measure. Whatever's left over is stuff that's just not accounted for by either individual difference or systematic change over time. that's just our error. We want to go back through and get this within subjects, and we could then just go through and take all of these are going to sum to, all these are going to sum up, and everything's going to add up to everything. There's no sort of random things that aren't getting counted anywhere in this design, okay? So when we're thinking about how we're partitioning variability in our repeated measures designs, think about taking our total piece of the pie, all the variability in this entire set of scores, and we're going to separate this first into a between subjects. This is our individual difference factor, and then our within subjects with this design is what we're interested in. Again, this is just absorbing the correlation between repeated measure, right? It's taking that out, it's pulling that individual difference stuff out, and all we're left with is just things that aren't systematically related to either our individual differences or repeated measure. So we end up with a much, much smaller error term than we would if we were to analyze this in a between subjects design. Okay. People kind of see what we're doing with this stuff and where this is going and why it ends up being advantageous in terms of hypothesis testing. Cool. All right. So some assumptions. We talked about one of the difficulties with our repeated measure designs is the layering in of some additional assumptions. These I made some changes to this slide. If this slide looks different than your slide, that's delete the stuff that was down below there. It's true, but confusing and not relevant to one-way design, so we'll ignore it for now. But we're thinking about our assumptions of our repeated measures ANOVA. Once again, normality in the distribution of sample means. Okay. John, what does it mean if I'm assuming normality in the distribution of sample means? What falls on a normal bell curve? Okay. Not quite. Not the population. Do I care about the? If I'm testing something doesn't have a normal distribution of the population, can I not use ANOVA? Yeah, you still can. So what is the normality distribution that for our means-based testing? If I say distribution, normality of the distribution of sample means.
All possible, the means of all possible samples from the population.
Exactly. We're talking about a sampling distribution, right? We're talking about central limit theorem, right? And so under what two conditions does the distribution of sample means start to become normal very quickly? If it's from a normal population, right? So if I'm looking at, say, intelligence, right? That's a nice sort of normal bell curve, right? So if I'm sampling that, distribution of sample means is going to approach normality very quickly. What's the other thing that we're concerned about? Big sample sizes, right? So even if I'm looking at, let's say Evelyn is looking at purging behavior or something like that, that's probably not normally distributed in the population, right? But if you've got, and when you assess it, if you just have a random sample of undergraduates, that's not going to be a normal distribution. Everybody's going to stack up to zero, and then you're going to have people with an increasingly severe purging, right? But as long as you've got a reasonably sized sample, so you've got cell size of 30, 40, 50, right? The sampling distribution of that is going to start to become normal very quickly. Remember that, again, here in this scenario, we're saying purging behavior has a distribution like that. That's not normal, right? And when I go through and I assess it, I'm probably going to, hopefully you're doing some screening, right, to get it so you don't just get a bunch of people with zeros, right? But when I'm talking about the sampling distribution, if I've got n equals 50, right, what's the mean of this sample going to be? I don't know, probably something here, right? And so if I go through and I repeatedly sample all possible samples of 50 from this population, right, on average, let's say this is a score of 0.5, okay? On average, the mean of my sampling distribution is going to be 0.5, right? Now, sometimes I'm going to grab samples that are real high. Sometimes I'm going to get samples that are almost next to 0. But the distribution of the mean of all possible means that I could pull from that are going to follow this normal distribution, okay? And so remember, this is the important thing when we're talking about a distribution or our assumptions for ANOVAs, repeated measures, ANOVAs, t-tests, and things along those lines. We're not concerned necessarily about what the distribution of scores are for your set. Your set might actually have kind of ugly scores, right? The distribution of my scores at time 1, time 2, and time 3 might be kind of funky, right? But I'm going to be less concerned about that if whatever I'm measuring should have a normal distribution of the population, or my sample sizes are reasonably large, so that central limit theorem says that the distribution of sample means is going to approach normality very quickly, even though the thing that I'm actually assessing is non-normal in nature. Okay. Now this doesn't give us carte blanche to just like run through and never be concerned about stuff, right? If I've got a really funky distribution and I've got cell sizes of 10, I should probably be concerned about that, right? Because one, I'm not sure that I haven't violated assumption of normality in the distribution of sample means depending on what I'm measuring. Also, if I have a cell size of 10 and I get a wacky score that's way above or way below anything else, what happens to the mean of that cell? What is it, Kaylee?
It just gets pulled in.
It starts getting drug around, right? Now, if I've got a score that's really high or really low and I've got a cell of 40 or 50, that one score, depending on sort of how extreme, probably going to have minimal impact, right? For the types of things that we typically assess. Now, if I'm an economist or a sociologist or something, I'm looking like something like income, and I get someone who's makes $4 billion a year, and then everybody else is undergrad, that's going to be a problem, right? But for the types of things that we're typically studying, unless you've got small cells, you're probably going to be okay and fairly robust to this type of stuff. So this is the type of thing that starts to come in when you're going through and you're doing your screening with this stuff. You know, I don't want you to just say, oh, there's extreme values or outliers, and so those are problematic, right? This is why I want you to be focusing on, tell me what the value is, right? What the value, the standardized score is that you've identified as potentially sort of extreme score, what score it's paired with, right? Because an extreme score in this sample might not be an extreme score in another sample, right? If I'm, you know, so for PTSD, if I'm looking at PTSD in university undergraduates, I might have a score that's sort of way out of bounds, right? Or really, really high. But if I was actually doing a study in an actual clinical sample, that'd be right around the mean, right? So this helps contextualize what values are identified as extreme values within your cell. And then in your summary report, wanting you to talk to me about, is this a thing, right? What I don't want you to do is just say, oh, this is robust to stuff, so it's not a big deal, or we saw sort of extreme values, but and so, yeah, these are extreme values. If those extreme values actually are just part of a continuous distribution, they just happen to be hanging out, of course, with on the tips. Wanting you all to be thinking carefully about, okay, I've identified things that are likely problematic values. Are they going to be an issue in this sample? To what extent should I be concerned about it for these specific analyses? And then talking about sort of why or why not, right? If I've got cell sizes of 5 and someone's 4 standard deviations of the mean, yeah, that's a problem, right? If I've got a cell sample of 30 and someone's 3.5 standard deviations of a mean, I certainly want to talk about that, but probably not going to have as big of an issue, right? If I've got a distribution that looks like this, and I've identified extreme values down here that are, say, z equals -0.3 or -3.6, I might think about that a little bit differently than if I have distribution that looks like this, and this guy is negative 3.6, right? That's a different situation than before, right? I've got here, we've got everybody, and then we've got someone hanging out way out here. That's a different thing than if this is my distribution, right? So these are the types of things when you all are doing your screenings, wanting you to take a look at, and it's because it's hard to just apply rules of thumb, right? The way you start to understand sort of whether or not this is a weird thing or not a weird thing is you just do a lot of them, and eventually you get a sense for, okay, this is something that's typical, or this is pretty extreme, or when you're, talking about your histograms or your box plots, saying, oh, this is part of a continuous distribution, and so we've got extreme scores on the end, but it's a large sample, we're probably not going to have a big thing, versus, well, it's a small sample, and we've got a discontinuous distribution where we've got a couple of values kind of separated from the rest. They're really high and really low. May or may not be a huge issue for these, but certainly want to check those to make sure that those are real values and not an error by a researcher system or something along those lines, that those are actual real values, right? Another thing that people have done, and this is a good thing to consider, right? Like, well, these are reasonable parts of sort of the thing that I'm measuring. That's a good thing to know, right? So if this value is reasonable, it's plausible value, it's sort of within the whole string of values that people could have, but that doesn't necessarily mean that it's not a problem, right? If I'm, again, looking at binging behavior, and I've got, here's my sample of scores, and then I've got some person way out here, right? That might be a score that's consistent. Like, someone could have that level of binge eating, so it's a valid score, and someone I probably want to keep in my measure because they're probably someone who I'm really interested in, but that score out there, depending on what this scaling is, might start to drag everybody out there, particularly if this cell isn't super large, right? Or if this value is really far out. If this is, say, a 0 to 100 scale, and most people are around 20, we got someone who's at an 80, yikes, that's dragging stuff out, right? And so wanting to be careful, just because this is a real value and something that could happen, that's not necessarily, that doesn't resolve or ameliorate the fact that that value or that case could still cause some problems, right? Because this is the thing, you don't want to have an entire study that's dependent on that person dragging that score way out there. Because if that's the case, then I don't have any confidence in your results. Because if you ever have a study where if you can like remove 2 or 3 people and it completely changes the results of your study, that's not good. Now it's sort of up to you to be courageous and sort of note that, because sometimes those 2 or 3 people are making the whole thing work the way you want it to, but in the back of your mind you need to have serious reservations about whether or not you found a real effect or it's just some artifact because you got a wacky person hanging out there somewhere in the end. Okay. Yeah?
Is that where like transforming the data will be helpful, bringing that person in and still giving them still letting them know that a value that is above others? Right?
Yeah, I mean, it sort of depends. We're going to talk about pros and cons of transforming. I was sort of loosening up on sort of this idea of transforming scores. But if I'm looking at something like binging behavior and I expect it to have a very skewed distribution of the population, or substance abuse outcomes or something along those lines, or reaction times or something like that, and we know have a skewed distribution, then transformation might just be part of the course. It might just be something that we do in this literature, and if you don't do it, it's going to look weird, right? Now, the bigger issue I see is people like, oh, I have kurtosis value that's not, or a skew value that's not 0, so I went through and transformed a bunch of goddamn stuff, and now I can't apply any sort of meaningful interpretation to anything. That's a problem, right? Here, if it's one score, I'd probably just smooth that distribution. I'd take that person and say, all right, I'm going to set that person to their value to be one unit higher than the next highest value in the distribution. As opposed, if it's one person, and this distribution without that person there still makes it look at least reasonable, right? I'd probably smooth that as opposed to transforming it. But if I have a long tail, something like this, I might then start to think about, okay, well, this is what happens. We'll talk about this as you're going through and trying to address stuff. Sometimes I bring this to here, but now all of these are now extreme values, and it's just an iterative process, right? So we're moving forward. And so again, it's going to depend on what you're trying to do, you know, how you're going to go about this, sort of what makes sense based on individual characteristics of the data. Yeah.
This still be applicable if like time 1 was baseline? So if
Mhm.
time 1 was really time 0
Mhm.
and like the independent variable hadn't, like treatment hadn't started,
Yep.
that still
Yep.
stayed the same?
Same thing,
Okay.
same thing, right? And so again, this is a long, extended conversation about wanting to make sure that you guys are understanding, because people will often forget, like, oh, these scores are terrible, so I violated my ANOVA assumptions, and so I got to do crazy transforms or something like that. No, that's not the distribution of your observed scores isn't the assumption. The assumption is that you have a normal distribution of sample means. Normal distribution of sample means occurs when you've got reasonably large cell sizes, or whatever you've sampled from has a normal distribution of the population, right? So unless there's something really wacky going on in my cells, I'm probably going to be okay, right? But and our designs are generally pretty robust to violations of normality in our observed variables. But when we start to combine these things, right? If my data has unequal shape and unequal variance, right? So if I've got time 1 scores have a strong positive skew, and time 2 scores have a strong negative skew, and variability at time 1 is 3 and variability at time 2 is 20, that's a problem, right? Because we've got my data are different shapes, they're going in different directions, and I've got violations of homogeneity of variance is going to be a problem. Unequal variances and unequal sample sizes. This technically isn't an issue for our one-way repeated measures, because you have to have the same people in each one, but again, something to remember, violations of normality in small sample sizes, right? That starts to become a problem. So really, when we start, when we're screening our data and starting to identify problems, it's because of combinations of things that start to make this all difficult. Okay. Questions on this? Okay. So normality in our distribution of sample means, number 1, but we've talked about that before. And then 2, homogeneity of variance across intervals. I think I had treatments on the slides, change that over to intervals just to make that clear. But essentially, we're saying that we're assuming that variability at time 1 is reasonably similar to variability at time 2 is reasonably similar to variability at time 3, so on and so forth. Now, SPSS won't give you a specific test of this in your repeated measures ANOVA. What we do is generally take a look at our Fmax. Okay, Fmax, remember, is the ratio of your largest to your smallest variance across your repeated assessments. Again, ANOVA design is generally robust to simple violations of homogeneity of variance, but if we start mixing that in with some other stuff, then things start to become problematic. Okay. Feeling good about recap on basic assumptions? All right. Let me get a clicker. Okay. So this is old stuff, new stuff that we need to start thinking about in terms of our repeated measures designs. For repeated measures designs, we also have assumptions about our variance covariance matrix. Okay, if we look down here, what we've got is a variance covariance matrix for relation and variability in assessment A, assessment B, and assessment C. Okay, so on the main diagonal, you have the variance of scores at time A, variance of scores at time B, variance of scores at time C. On the off diagonal, these are your covariances, right? This is just your raw metric of the extent to which A and B vary together, A and C vary together, B and C vary together. This sigma hat matrix right here, if we were to find that the variances of our measurement at time A and time B and time C are all equal for all intents and purposes, and all of the covariances across each one of our assessment points were equal, we would say that this matrix meets the qualifications or the assumptions of compound symmetry. Okay, so basically what this is saying. So someone tell me, how do we understand covariance? What is covariance? Laura?
When time A changes, time B also changes.
And what can we do to covariance to put it into a more interpretable metric? Yeah, right. So basically, this is just a raw, unstandardized form of correlation, right? So if it helps, if you want to say, basically, that the variance of each one of our time points are identical, and all different time points are correlated equally with all other time points. Technically, the assumption is about your covariance, but covariance is just a measure of the extent to which A and B are related, or A and C are related, or B and C are related, right? So if we've got a matrix that is evidencing, we have evidence of compound symmetry, we're saying that in the population, variances are all equal across assessment points, and basically all assessment points are related to all other assessment points in the same way. Okay? If we standardize this variance-covariance matrix, we get a diagonal of standard deviations and off diagonals of correlations. Okay. This is a nice way to keep in your mind conceptually what covariance represents. It's the same thing as a correlation. It's just a correlation is standardized. Covariance is just an unstandardized metric of variability. Okay. So people understand what we're assuming with compound symmetry. So now the good news is that compound symmetry is a pretty strict assumption, and it's not necessary for our repeated measures ANOVA. Okay? So when you're looking at methodological stuff on repeated measures designs, repeated measures ANOVA, you'll see this idea of compound symmetry. People are talking about compound symmetry, this is what it is, right? Now the good thing is that we don't necessarily need to have that in order to not violate our assumptions. But what we do have an assumption of is a term we're going to call sphericity. Okay, and we would say that a variance-covariance matrix demonstrates sphericity if the difference scores of each paired repeated measure have equal population variance. Right. So basically, we're saying that if I take scores at time A and subtract scores for an individual, if I take scores at time A and subtract them from scores at time B, and look at that difference, we're gonna see the same level of variability in those scores as if I took scores at time A and subtracted them from scores at time C, and that's gonna be the same. So here, let's say for this, A minus B, B minus C, and A minus C for 1, 2, 3, 4, however many people I have in this sample, right? If I take a look at to take the difference scores for each one of these time points, and I want to look at the variability across each one of these. If I say the variance is identical across each one of these pairs, then I would say that this matrix meets the assumptions of sphericity. This is a formal assumption of our repeated measures ANOVA. And so what happens if we start to violate this assumption of sphericity is we get F ratios that have distributions that are very different than what we would expect under a standard F. So basically, the same problem we have with any violation of assumption. Our test statistic doesn't follow the theoretical test statistic that we're testing it against, right? We've got a distribution of a test statistic, it's just not following an F or a T or a chi-square or a Z or any other such thing, right? And so this starts to be a problem, because if I'm saying, oh, this is the probability of obtaining this score in an F distribution, but whatever I'm measuring doesn't actually follow an F distribution, I lose all my confidence in that, so I'm actually sort of drawing reasonable inferences based on my hypothesis test. Okay? So what we find is that we can have a variance covariance matrix, right? We can find sigma hat meeting criteria for compound symmetry. If it meets the criteria for compound symmetry, it'll meet criteria for sphericity. But I may have matrices that meet requirements for sphericity that don't meet criteria for compound symmetry. Okay. Questions about this? Keep kind of seeing the difference between, so if we're talking about compound symmetry, we're saying variances are all identical and that the covariances are all identical. That's compound symmetry. Sphericity just says the difference between each of our assessment points, the variability of the variance of each of the different scores of each of our assessment points are sort of roughly equivalent across our design. Thumbs up if you got a handle on this. Okay. So, why this is a problem? Okay. Now note that this sphericity assumption, I've said that this is a new thing for a repeated measures design. Sphericity is actually also an assumption of our between subjects ANOVA. We just don't worry about it, right? Because what do I expect my covariances to be in a between subjects design? If this isn't 3 repeated measures, let's say it's 3 conditions, what do I expect all the covariances to be here? Do I expect condition 1 to be correlated with condition 2 to be correlated with condition 3? No. By design, these are all functionally equal to 0, right? So my assumption is still there, I just don't have to worry about it because I've got my independence assumption, and that means that I'm still worried about my homogeneity of variance, right? I want these in the diagonal to be roughly equivalent. I'm just assuming everything in the off diagonal is 0, or in the off diagonal is 0, and so I don't worry about it. We don't worry about this on between subjects designs because we're assuming that we haven't violated our independence assumption, right? But with our repeated measure ANOVAs, we expect our covariances to absolutely not be 0, right? In fact, we're kind of counting on the fact that they're not 0, because if they are 0, then we lose all the benefits and power of a repeated measure design, right? If your repeated measures are correlated 0 with one another, you're functionally running between subjects ANOVA, right? You've lost all benefit of the repeated measure design, right? And so because with repeated measures ANOVA, we're assuming that our covariances aren't 0, so now we have to go through and start to become concerned with this sphericity assumption that's been there all along. We just ignored it because by design it's not an issue, okay? Now the problem is for our applied research, the type of stuff that we do, our sphericity assumption is almost always violated, okay? We are never going to go into a situation and we're going to say, we just assume that we met criteria, that we met for sphericity here, okay? And the issue is that if I've got a repeated measures design, particularly with any sort of distance in between our repeated assessments, what we're going to find in general is that measures that are made closer in time are going to be more tightly correlated than measures that are more distant, right? So if we think about, I'm doing a developmental study where I sort of have a measure in infancy, young childhood, sort of middle school, high school, sort of young adulthood, right? I probably expect whatever I'm measuring at these 2 time points to be more closely related to something I'm measuring here and here, right? And because of that, what we find is we find that our adjacent assessments, or the different scores in our adjacent assessments between A and B, we're going to see less variability than I'm going to expect in the difference between A and C, right? And because of this, it means that this variance is going to be much less than that variance, and what we've done then is we've got a violation of our sphericity assumption, right? Now this starts to become maybe less of an issue if, you know, I'm measuring things one right after another. So if I'm in a laboratory design where I'm measuring your physiological response or your emotional response to some stimuli right now, and again 5 minutes later, and then another 5 minutes after that, A and B are probably going to have similar correlation as B and C and A and C, just because everything's kind of occurred in a pretty close time. But if I'm looking at something correlating over, if I'm looking at your mood over 3 assessments made over the span of 15 minutes, those are all probably going to be pretty correlated, versus if I go through and I'm assessing mood week 1, week 2, week 3, week 4, right? But even sort of on that short time frame, we're still assuming that if I ask you right now and 5 minutes later, that's the correlation between those 2 scores on average is going to be stronger than the correlation between scores right now and 10 minutes later, right? And so this is where we get our violations of sphericity, just because things that are measured closer in time on average tend to be more tightly related. We're going to see less variability in the different scores than things that are measured over longer periods of time. Okay. So people, to get a good conceptual understanding of sort of what this sphericity issue is and why in practice we're almost certain to violate this in all situations. Okay. So what do we do about this? We know what's going to happen. What do we do about it? Well, fortunately, we have some corrections to help sort of bring this back into line. Moxley provides a test looking at deviations from sphericity. We'll see this on your ANOVA output. Problem is Moxley's is underpowered. It's typically not a very strong test. And if my test is underpowered, hey, what is that? What is it? What are the implications if my test of sphericity is underpowered?
Would that just make it more likely that you would get a type 2 error?
That's true from a practical standpoint. So yes, absolutely right. But from a practical standpoint, I have a test of sphericity. The problem is my test of sphericity is underpowered. What's the problem with that? What is that likely to lead to? From like a practical standpoint, in my decisions about whether or not I need to correct or not to correct for tests.
Oh. If it's underpowered, then it's telling you have get a better result, I guess.
Yeah,
than you
right.
actually do.
If it's underpowered, it's basically telling me that I don't have evidence of a clear violation of sphericity, right? So I'm like, cool, don't have to worry about it. But the test itself is underpowered, right? And so basically we have a test that flags us when we have things going wrong, but it's a crappy test and doesn't tell us that we have a problem when there's probably a problem there, right? So we've got underpowered, and then also sensitive to violations of normality. If my measurement of A and B or B and C and A and C are not normal, and my different scores are normally distributed, then it starts to throw the test off. And so there is a formal test, but what we're going to do in practice is ignore the test and just proceed on to our corrected tests. Okay. So again, just keep an eye out. If you see someone who's done a repeated measure design, like, oh, sphericity wasn't a problem here, so we just went through with uncorrected tests, that should just throw a flag. They better have a damn good reason for why this is an issue, because at this point, practice is just to sort of move forward as if, assuming that we've always made this violation. So, corrections for sphericity. just like before. Well, same thing when we're had violations of homogeneity variance assumptions for our t-tests, right? We're assuming that whatever test statistic that we've derived still follows a t-distribution. You just don't know what the t-distribution is, right? So we have to kind of guesstimate what family of t-distribution that is, right? So with our Levine set, or with our correction for homogeneity of variance, we're testing against a different degrees of freedom than we have. Usually it's a downward correction on this stuff, right? Same thing with our Fs. We're just going through, depending on what correction we're going to use, we're going to test our test statistic against a critical value with a different degrees of freedom that are indicated by our test, and that adjustment based on the extent of the violation of our epsilon. Epsilon, if we've met our sphericity assumption, epsilon equals 1. Is that epsilon? No. Is that epsilon? Okay. Yeah, epsilon equals 1. Sphericity assumption is met. But as our violation of sphericity increases, epsilon is going to decrease, and the penalty we incur for that violation is going to become increasingly severe. Basically, we're setting the benchmark farther out to claim statistical significance based on this correction. Okay, so a couple different corrections we have. Greenhouse geyser correction. This is a downward adjustment for our degrees of freedom based on the greenhouse geyser variation of epsilon hat, right? So the greenhouse geyser formula has a specific way in which it's estimating epsilon, and then depending on what that value is, sort of making the adjustment based on that. Hunfeld has a different correction. Estimates epsilon slightly different, and so the idea is that, oh, we can use this if the true value of epsilon is above, greater than, or equal to 0.75. Hunfeld, you'll see this generally assigns less of a penalty from greenhouse geyser. Greenhouse geyser is what people would typically use in terms of being conservative. Again, another thing you need to remember is these designs are incredibly powerful, particularly if you have reasonably large cell sizes. And so there's some recommendations to say, you know, if your uncorrected test is reliable and your greenhouse geyser isn't, maybe using Hunfeld as sort of an intermediary, this is just going to keep you out of trouble. Greenhouse geyser is kind of the field standard in terms of corrected statistics for this test, so just probably just use this one, okay? Also, Helmut's that the Hunfeld correction in SPSS and SAS isn't corrected in any way, so all the more reason not to go through and utilize that correction. Or if you do, just make sure that you go through and hand calculate it, because the one that SPSS is giving you isn't any good. Questions about what we're doing to go through and address this issue are assumed violation of sphericity in these types of designs, yeah.
Do you still have to do corrections if like all of your time 1, time 2, and time 3 are all within like 15 minutes?
Yep, and you go through and I mean, again, even if it's all within 15 minutes, you're still going to go through it. And you can go through and take a look. You can look at this empirically. We're going to do this in the handout. I mean, just it's kind of a descriptive way. Just look at the correlations, time 1, time 2, and time 3, and see what they look like, right? And generally what you're going to find is that there's clear differences there. And so, again, you would have to have a really, really compelling argument for why you're not using a correct test. And if I was reviewing your manuscript, I would say, well, it sounds to me like your corrected test weren't statistically reliable and your uncorrected test was, so now you're kind of trying to come up with some reason why you don't have to use that corrected test. In most cases, if you've got a good solid effect, you can recognize that these are just incredibly powerful tests. If your uncorrected tests are statistically significant, your corrected test should probably be pretty close as well. Yeah.
And the epsilon index itself, is it 0 to 1 or?
0 to 1, I mean, again, we don't worry about it too much because, again, the assumption is that we've violated it. So, I mean, SPSS will give you the greenhouse geyser epsilon, the Hunfeld epsilon. That's not correct. This one is. But I don't know that I've ever seen someone actually report epsilon just because it's assumed that you violated it anyway. I mean, this is kind of an easy thing because it's something that you need to know about and it's something that comes up. But this is one of those cases I try and tell you not to sort of just rules of thumb. This is a rule of thumb. You just assume that you violated and proceed to correct the test anyway, and just don't worry about sort of this stuff. At one point in time, people were really worked up about sphericity violations and how you address that. And if you use corrected tests or multivariate tests or things along those lines, at this point, no one worries about it. You just assume that it's violated. You just proceed with the corrected tests and just interpret those. Cool. So, conceptual summary, or repeated measures ANOVA. We've got, if we have people who are observed only at one time, right, or between subject designs, all the variability due to individual differences, all that gets chalked up into error, right? That's all just stuff that we haven't accounted for. But when we've gone through and we've observed people, the same people, over successive periods of time, what we can do is we can estimate sort of those individual differences. We can say, all right, well, this is just due to people are different. We can suck that out and parcel that out of the error term. The greater the difference that we see across people, higher correlation across treatments, right? If everybody has about the same score across each one of our assessments, right, we've got no variability at time 1, we've got no variability at time 2, we've got no variability in our scores, what happens to our correlation? Goes away, right? But we've got a lot of variability across individuals. There's a lot of opportunities for A to relate to B to relate to C. Think about it this way. If my scores at time A are all really tiny, right? And my scores at time B are all really tiny. What's the correlation of that dot there? Next to 0, right? But if I got a lot of variability in time A and a lot of variability at time B, what's that correlation? Much stronger, right? And so this is the thing, we talk about variability as error, but in terms of looking at the relation between variables, we have to have variability. If I have restricted range on anything that I'm trying to run a correlation on, it's gonna attenuate my correlation, it's gonna kill it, right? So it's good if we have individual differences, because those individual differences are gonna get sucked out, right? And the higher the correlation that we have across treatments, the stronger and the more powerful this test is gonna be, okay? So again, my dissertation, I went through and was collecting some physiological measurements, some skin conductance, and a couple other things, and all measured across a period of, maybe like 5 minutes, sort of 1, 2, 3. Those measures are all correlated like 0.9 with one another or higher. This is really strong. Now, the individual differences across people, some people come in real high, sometimes people come in real low. Sometimes people come in, you have to scrub them down with a Brillo pad to actually get a signal, because undergraduates are grimy sometimes, right? But because of the strong correlation, you should start to go through and sort of tease out very, very subtle effects, right? So to the extent to which your repeated assessments are correlated with one another, that's going to lend itself to increased power of your test. Came in with Adam's dissertation too. He's got a repeated measures design, but Ben helped us out with this, right? But in terms of trying to power, how many people do I need per cell in order to adequately power my design? Biggest piece of that is how correlated your time points are. He went through based on preliminary data that he had expected. He had proposed, I think, like 160 people. So 2 different conditions. It was a 2x2 mixed design. So you got 2 conditions, measured on 2 assessments, right? And he had sort of said, 160 people, 80 people per group, I guess, right? But based on first semester data collection, you got like 40 people. That's not great if your target is 160, right? We looked at correlation at time 1 and time 2, about 0.9. we throw 0.9 in there and it says, oh, you need 40 people for the whole study, right? To detect the interaction he's looking at, right? So now you don't want to just say, oh, I'm done collecting data because I like the results and I'm going to quit now, right? But sort of getting an accurate estimate of that correlation. Now, if you drop that from 0.9 to 0.8, then it jumps it up to like a sample of like 60 or something like that. Still reasonable, but start to have a pretty big impact based on the correlation between your repeated measures. Okay, so but this is kind of what's going on with that. How are people feeling about this? Feel like you have a good headspace for what we're trying to do with these different analyses. Okay. So let me see what time is it. It's a good break time. What we'll do, go ahead, take 5-10 minutes. We'll come back, we'll jump into an empirical example here. So make sure I posted a couple data sets. Make sure you got those up and running when we jump in, when you finish up. That you want to be thinking about in terms of with your repeated measures designs. Whether or not the repeated assessments have some, whether the order is meaningful, okay? Sometimes it's going to be and sometimes it's not going to be. So we've got two different examples here, and so the answer to that question is going to determine your approach for interpretation, follow-up, so on and so forth. Two different examples here. So this first one, we're looking at, we're going to say we have inpatient depression scores, right? And what we're interested in is seeing, the question is whether or not the pattern of depression scores changes over the course of a 6-week inpatient treatment. So we've got BDI-1 intake, BDI-2 depression scores at 2 weeks, 4 weeks, 6 weeks. Okay. Does order make a difference in this these data? Yeah. Why is that, Haley?
Sorry, because you're treating them, so you want to see a difference at the end of treatment versus
Yeah. I mean,
somewhere?
you've got a natural progression, right? So like the ordering of time makes a difference, right? I can't just scramble these up and sort of have it make sense, right? So in this example, order makes a difference. Here, in this second study, what we did is we collected data on this and interested in whether or not willingness to maintain friendship with a hypothetical victim of some sort of life stressor, whether we see differences based on the nature of the event, right? Now in this study, when I'm starting to think about this, I'm like, boy, I wonder if people's willingness to reach out and maintain friendship for people who are survivors of sexual assault is the same as, say, combat deployment, or whether or not people on average are more likely to provide friendship for people who are survivors of traumatic events versus other stressful, but things that we would probably say are non-traumatic events, things like I lost all of my savings, or I had to relocate for work, or I had a partner who was unfaithful to me, or something along those lines, right? Now my problem is I want to go through and I'm like, oh, I want to tease this apart. But if I just get one group of people and say, all right, you read sort of this vignette about someone who was exposed to sexual assault, and then another group of people read the measure or the vignette that relates to combat, and another people read a vignette that's related to infidelity, and someone else reads a vignette and gets scores for work. Okay, how many people am I going to have in this design to test all of this? A lot, right? Because one, we're going to have huge variability, and then two, maybe we won't, because we're also asking people a loaded question. Like, how much are you willing to provide friendship to someone who has something terrible happen to them? Where everybody going to score? On a high end, unless they're a jerk, right? And so thinking about how do I do this without needing 5,000 people to detect an effect? Well, answers are repeated assessment, right? So I go through, and instead of having different groups of people respond in between subjects, I just have the same group of people respond to different vignettes. Now for this one, again, one of the things we want to think about in terms of analyses like this is a concern about carryover, right? That's a limitation of repeat measure designs. If I ask someone, probably makes a difference the order in which I present these probably has some sort of impact on how people are gonna respond, right? What do we do to address that? Counterbalance, right? Then with 8 of these, you know how many different possible combinations of 8 sequence? It's a lot. I probably went overboard in sort of writing off different, printing off different forms and things like that. But if we go through and counterbalance that way, functionally, sort of the order in which you get these is going to be random, and starting to sort of measure some of that stuff out, right? So these are our 2 examples. So let's start with inpatient depression. So if you open up the data set that is repeated measurement at ANOVA exercise ordered means, and grab your sheet right here, right? So what we've got is we have just a group of individuals who we're looking at BDI scores at time 1, time 2, times 3, and times 4. This is intake 2 weeks, 4 weeks, 6 weeks here. Okay. So what we're going to do, I'm going to first go through and sort these just to see. We're not going to worry about screening too much here with this. All right. So I just see that I have full data available for all of my people. I can go through and I can go analyze descriptives. And I can say, just take a quick look at sort of my skew kurtosis values. Okay. So all my values are in bounds. Right? If it's 0 to 63, so I don't have anybody who's way out of bounds. My skew looks like it's, my indices don't look like they're too bad. But this is another thing too, wanting to be careful in your interpretations, right? Not following onto that rule of thumb. What see sometimes people say, oh, well, I don't have a problem with skew because my skew kurtosis values are less than or around 2. Then you look at your actual histogram, and this is probably going to be pretty, we can take a look, that's probably going to be a pretty substantial skew, at least visually. If we go histogram at 6 weeks, it's hard to argue that that's normal or approximating normal, right? Because if you try and tell me that is based on the skew index, I'm going to tell you nope, right? So wanting to make sure when you're interpreting these to distinguish between a level of skew, like so the skew indices, formal indices of skew is less than 2, suggesting that we don't have sort of violations to the level that sort of are going to be problematic necessarily, right? But then you can still look at the histogram and say there's still evidence of a positive skew with, you know, some values that are falling away from the rest of the distribution, some very high values here, right? So just being careful as you're going through and interpreting. We don't want to just look at the number and say, oh, this is problematic. It's not, at least for the stuff going on here. And then when you're doing your write-ups for actual publications and work like that, it's probably better to talk about this as it is suggesting, failed to indicate strong evidence of problematic violations of normality or something like that, as opposed to, it's hard for me to argue that that's approximating normality because it has a skew value of less than 2, okay? So just being careful with those rules of thumb. But what we're gonna do, we're not gonna go through and do formal screening on this, but what we will do quickly is go through and take a look at our correlations. Why might, Layla, why might we be interested at correlations across weeks 2 to 6? Okay, so here we don't have a manipulation on it. We're just following people over time as they're receiving treatment, right? But yeah, you want to get a general sense of how tightly correlated these scores are, because that helps determine why not organ music, why not a power drill? Jesus, I can't escape it. what else from a technical standpoint might we be interested in gleaning from this correlation table?
Covariances.
Yeah, covariance, sort of the extent to which these measures are correlated with one another. And John, if I'm looking at that correlation table, would I suspect that I have a violation of sphericity here?
Yes.
Yeah, why? Yeah, so the off diagonals aren't all the same, right? So my correlations aren't all the same. And what, Emilio, are we seeing going on specifically in this pattern of correlations?
Are there getting less of correlators going?
Yeah, right. As our measures get more and more distant, the correlation between our measures gets weaker and weaker, right? So basically, we're seeing exactly what we expect to happen in designs like these, right? So if we look at the correlation at intake in 2 weeks, that's a much stronger correlation than the correlation between intake in 6 weeks. Correlation between 4 weeks and 6 weeks, much stronger than the correlation between 6 weeks and 2 weeks, right? So we're seeing exactly the type of systematic difference in how these measures are related to one another that would be consistent with our concerns about traditional violations of sphericity and things along those lines, okay? So, but we're not too concerned about that because we have ways of dealing with it. So what we're gonna do is we're gonna assume that we've gone through, take a look at violations of the normality of our sample distributions, right? So we're going to go through, take a look at our scores at each one of our time points, and then go through, run an F max, look at variability across each time point, right? So we go through and take a look at that. We're going to say, yep, we got violations of sphericity, we expected that. And so now we're going to go then and say, okay, we've decided in theory that these data are at least reasonable to assess using our one-way repeated measures ANOVA. So we're going to go to Analyze, and we're going to go down to General Linear Model. Not Generalized Linear Model, just General Linear Model. We're going to go down to Repeated Measures. Let's pick this, okay? So what it's going to ask you to do is it's going to ask you to define your repeated measures factor, right? So what we're going to do is I'm going to name this, I'll just name this time. And I'm going to say how many levels to time. We've got 4 assessments, so I'm going to say 4 levels. I'm going to hit add, okay? And so this is just saying that we've got one repeated measure factor. It's got 4 levels, and we're going to name this time, okay? Then we'll go through and define. It's going to take us to a new window. What we want to do with our new window is go through and under the within subject variables, our time variable, plug this in, making sure that we've got our order right, because we've decided that for this study, the order of assessments is going to be important. So we go through, drop that in. In terms of between subjects factors, this is just a one-way repeated measure, so there's nothing there. We don't have any continuous covariance we want to worry about, so we're good to go in terms of not needing anything to fill into these boxes here. Model. This is where you can get technical about how you're calculating sums of squares and things like that. We're not going to worry about that. Contrasts, we're just going to leave that alone for right now. Plots, let's plot time on a horizontal, right? And so this is just going to measure mean at time 1, 2, 3, and 4. Going to pick that over, hit add, hit continue there. Postdocs. Nothing to post hoc because all we have is a repeated measure factor, so we're not worried about that. Save, options for saving different types of things, we're not going to worry about that. Options, this is where we can start getting different means for different things. We'll go through and have it display individual marginal means for time, although we won't do anything really with this, but we can request descriptive statistics, estimates of effect size. We'll request a homogeneity variance test. It won't give us anything here, but we'll request it anyway, just so you can see what's going on there. And then we'll leave it at that. Okay. Hit continue, and then if you go ahead and hit paste, so this is what you can see the command to run this. All right, through and we run it. Get a warning at the top telling me you can't run a homogeneity variance test because I don't have one group, right? So there's nothing to test homogeneity variance on. SPSS won't test homogeneity variance with across your repeated treatments. You have to do that on your own with an F max to determine whether or not you think you have a problem there. But here we've got our measures. Once again, always want to go through and make sure that you're taking a look at this to make sure that your repeated measures are what you think your repeated measures are so that you haven't made an error there. We've got our descriptive statistics telling us how many people we have and the means at each level, the sample sizes in each one of those, right? Wanting to make sure that all matches up to what we think should be going on. And Layla, if we take a look at this descriptives table, what is this suggesting to us?
That over the course of us assessing BDI, scores from 8 to 6 weeks, the scores are increasing.
Yeah. Descriptively, it looks like things are getting better over time. Now, we haven't run our test, but at least this pattern of means is doing what we would probably expect it to do. Also, anybody, what might increase our optimism in that this is going to be a statistically reliable trend? What do you think, Laura?
Standard deviations also decreasing.
Maybe. What else is maybe a big hint that maybe this is going to be wildly statistically significant?
Sample size?
Yeah, close to 400 people in this. That's it would be almost impossible not to find something in these data. Okay, because remember, our question here is there variability in the pattern of means over time, right? So this isn't a test in and of itself. Our omnibus test isn't going to provide us a test whether or not things are increasing or decreasing. It's just telling us whether or not things are different across the course of these assessments. So we're feeling pretty good about this. Now we drop down, we've got this table here for multivariate tests. You're going to ignore this, okay? This has to do with a different approach to evaluating repeated measures. A multivariate approach is a different way to do it. There's some sort of nuances. For our purposes, don't worry about this. You're not going to go through and test this at all, okay? Now, don't, because you're going to see F tests and significance values and things along those lines. Ignore this. Don't get hung up and give me F statistics from this table because you're going to be off base with stuff, okay? Now, we go down and we see underneath this are Moxley's test of sphericity. And again, if we go through, we take a look, we see that's statistically significant, telling us that we violated our sphericity assumption. Do we care about that? No, because we've assumed that we're going to violate it anyway. Here are our epsilon values for greenhouse geyser, Hunfeld. Here's a lower bound epsilon. Again, you know generally what those are referred to, but we're not going to go through and interpret those or make any, put any interpretive value onto that. Again, know what this is, but know that we're just automatically going to assume that we violated sphericity and jump down into our test of within subjects effects. Okay. Now, if we drop down to our test of within subjects effects, we will see that we've got a number of different options here. So it looks like our regular ANOVA table, but we've got some repetition here. In this first line, this is our sphericity assumed. This is the test of our within subjects factor, assuming that we haven't violated any assumptions of sphericity. Are we going to interpret this, Ella? Do we assume that we haven't violated sphericity ever? Do we assume that we violated sphericity, or do we assume that, oh, we're probably good and we don't need to worry about it? We assume we violated it, right? So this is a test as if we hadn't violated sphericity. But we assume that we have, and so we're going to ignore this, okay? You'll then see below this your greenhouse geyser correction, your Hunefeld correction, another correction provided here through SPSS. So what we're going to do now for this one-way design, our app tests are all identical, so it really doesn't matter. This will start to change as we get into mixed designs, but what we're going to do is always just report our greenhouse geyser F significance and effect sizes and things along those lines. Okay. So here is our effective time and then our error. All right. Now again, remember that for our repeated measures designs, for repeated measures designs, we're starting with our total, in between, within, repeated measure, error. So, Nick, which sum of squares is this one for our effective time? Where does that fall on this situation here? Which one is that? What sum of squares does that correspond to? What's that? This one right here? Okay, look at sort of so this is the main effective time. Where's that going to fall?
It'll be your within some.
Close. Keep moving. The repeated measures. Okay. So this is our main effective time. Remember, we named our main effective within subjects factor time. So this is our main effective time. This right here, we're going to interpret the greenhouse geyser. This is our test, our omnibus test of the extent to which our mean value of our repeated measure differs across assessment points. Okay. So all this is saying is, we got pretty clear evidence based on these data suggesting that over the course of these 4 assessments, we're seeing reliable variability in mean scores across these 4 repeated assessments after we've pulled out all the individual difference variability for individuals. Okay. Does this tell us how our measures are, how our means are changing? No, it's just saying that it does, right? So all this is saying that. And you also want to be careful here because this technically isn't a test of individual level change, like in HLM or something along those lines. All this is saying is that I've got 4 repeated measures. Do I see variability in the means of those 4 repeated measures, right? It's not a test of linear change. It's not a test of within subjects change necessarily. It's just saying, do I see variability across these 4 repeated measures? Sometimes you get into, if you start talking about it as, a trajectory of change or something along those lines, people get, understandably, so to say that's not a correct interpretation. We're just saying, if I measure it this time and measure it this time and measure it this time and measure it this time, my null hypothesis is that those values are all identical, right, within the population. This is saying that, nope, we're seeing variability across our repeated assessments so that at least one of these assessments is different than another one somewhere in there, right? Same type of interpretation that we would have with our one-way ANOVAs, our between subjects, is just now we're talking about repeated measures within people as opposed to differences across groups. Okay. If you want to kind of get a handle on that, okay. So looks like we do have clear evidence for a statistically reliable effect, and we see you're seeing differences in our repeated measures over the course of assessment. We're going to ignore, or if we go down here, okay, now we've got our error term, all right? I guess I labeled it. But this specifically, note that this is all you tested within subjects effects. So all of this is this stuff going on over here, this part of the of your partition, right? So you've got your repeated measures, and you've got your error. This is going to be your error term here, your mean squared error, things like that. Okay. We're going to ignore our test of within subjects contrast for right now. Okay, we'll get into that in a moment. But down here, you see your test of between subjects effects. this is what you have going on over here. This is all your individual difference variability that you're pulling out of this design, okay? Here, because we don't have a between subjects factor, there's nothing to really to test. This is a test of your intercept at the very basic level. This is just asking, do people's average scores across these assessment points differ from one another? Very clearly they do. It's a F of 11,500, or excuse me, 1,158, right? So that's a lot of stuff going on there, right? But this is just capturing all that individual different stuff and pulling it out, okay? But it's important to know where these different components are coming from, because it's going to be start to become relevant to calculating effect sizes for your repeated measures designs. Okay. So people comfortable with what we have going on here? So our main effect of time here is saying that yes, our repeated measure, our repeated assessment is changing. That the mean of our repeated measure is different. At least one value is different from another one over the course of our assessment, right? Now, if we go down, we have a plot of our means here, and these are our marginal means. They're going to be the same thing as our observed means here. It's very clear to see kind of what's happening here, right? But to this point, at least in the things that we've talked about, we don't have a strong test of what's actually happening in this situation. We just know that there's a reliable difference between at least two of these means. Okay? That's all we can say based on that main effect of our repeated measure that we saw above. Okay. People sort of understand sort of what we did with this very simple, just this one way repeated measures ANOVA. Evelyn, you got this down?
Mm-hmm.
You're just knocking thesis analyses out of the park right now.
Literally.
Okay, cool. All right, so let's change things up a little bit and open up with this other example, right? Other example is we've got a different situation where we've got unordered means. Basically, we've got 8 different vignettes that we had people come in and respond to. Okay? Does the order matter in terms of these vignettes? No, right? I counterbalanced them, so they're all scrambled up anyway. For these analyses, it doesn't make any difference whether or not one is I enter one before the other or any of that. I'm just interested in taking a look and saying, do I see differences across responses to this vignette? So I'm going to go through and open up the belief rating set. And before I start running things, I'm going to go through if I have any missing values or anything that. Missing value, someone figure it out. All right, so I'm going to go through graphs, analyze, descriptives. Yeah.
We're missing some pieces for class.
For class, okay, that's fine. We don't have to worry about, we're not going to put class in there yet. So just the 8 different vignettes. As for skew kurtosis, okay. All right. Now, this is a good thing to take a look at. So it looks like these are running on a 0 to 8 scale, right? So all of our values are in bounds, right? Whoa, what are people seeing here? Kate, what might I have some concerns about in terms of these data?
The skew.
Yeah, the skew. Yeah, what else?
The kurtosis, skew.
Yeah. My distributions are terrible here. Like really, really terrible. If we go through and we take a look, let's say, okay, we'll go through and take a look at people's rating 0 to 8, whether or not they would be willing to provide friendship, maintain friendship with someone exposed to sexual assault. So if we go down and find assault, that's not a great scale, right, in terms of distribution of stuff, right? We've got a horrible, horrible negative skew going on here, right? What's my saving grace here?
Over the direction.
Yeah, if I go down through and I take a look at the direction of my skew, I've got substantial negative skew for all of these, right? So the shape of my distribution, it's all garbage. It's all garbage in the same way, right? So I'm feeling that's at least something I can bank on, okay? What else?
Sample size.
You know, my sample size is massive, right? Because remember, the assumption of my test is that the distribution of sample means is reliable, or is normal. Now, our ratings of willingness to provide friendship to survivors of different types of horribleness and tragedy, is that something that's normally distributed in the population? Probably. No, right? But given sample size of 230 people, the sampling distribution of this still becomes normal, right? At samples of this size, right? So this is certainly something I'm going to note, right? And it's certainly something I want to be aware of, right? And this is also something that makes sense given the data and what I'm asking people to do, right? So I'm not necessarily shocked by it. That doesn't mean it's okay, but the combination of the fact that it's all looking like it's going the same direction. I've got a really, really massive sample. And then 3, if I'm looking at my standard deviations, I don't know, I square that. If I look at my calculated F max, someone tell me, someone with the calculator, someone take 1.351 and square that.
1.825.
And then take 0.77 and square that.
0.593.
0.593. All right, and then someone else with a different, Layla, you've got a calculator. Take 1.825 and divide it by 0.593. Tell me what that is.
Divided by what?
1.825 divided by 0.593.
3.077 or 7.
3.08.
Yeah.
Yeah, okay. So our F max is, we've got some difference in our variability, right? Across these different assessments, but I don't know if I'm super worried about it necessarily. Again, we talk about F max at 3 or above can start to become problematic with unbalanced designs. This is not an unbalanced design, it can't because it's a one-way design. So I'm probably overall gonna say, yeah, these data aren't great, but it's not something that necessarily precludes me from moving forward with my repeated measures, my planned repeated measures ANOVA, because one, my data is all sort of garbage in the same direction. My distribution of sample means is probably having a violation given the size of my sample. Some evidence of differences in variability is about my largest the variance of my the variance at my the greatest variance of my set of these measures is about 3 times the size of the smallest variance. Not optimal, but probably not problematic for these data, right? So even though this is a situation where things are looking kind of ugly, you can still probably proceed these data are probably going to be robust to these general violations. Okay. Now, I could also go through and say these all are skewed to a sufficient extent that I am just more comfortable transforming these data. And so I could do that. It's a negative skew, so I'm going to have to reflect and then go through and transform that, probably with a log transform or something like that. If I want to do that, that's fine, but now all of a sudden I've got a complicated situation where down is up and up is down because I had to reflect, and now I've got the log transform of an ordered categorical scale that means nothing. And so it starts to become, I can choose to do that, but it's incumbent on me to make sure that I'm interpreting this appropriately, because I'm no longer looking at differences in people's ratings or people's vignettes ratings. I'm looking at differences in the log transform, the reflected log transform of people's ratings. So I have to weigh pros and cons of that and stuff. So these are data that very well could be. I mean, if someone has told me that I'm going to go through and transform these, I'd think, fair enough, that seems like reasonable. I mean, it's not unreasonable, but it's not imperative for these data, I wouldn't say. All right, so going through, taking a look at that. But again, what we're going to do here is we're going to go down to analyze, general linear model, repeated measures, okay? And so now this is a big one. So what we're going to do is we're going to go through, and we can go through, look at correlations. You see, obviously, on the handout, we won't pull it up here, but you see different, clearly not constant correlations across all of these different events. So there's stuff going on there. But what we're going to do is we're going to go through and say, all right, I want to see if we're getting differences across these repeated assessments, across these different vignettes. So I'm going to name my within subject factor vignette. I'm going to say there's 8 levels because there's 8 different vignettes that we're giving people. I'm going to add that. I'm going to go define. And now what I'm going to do, just because it's going to help me keep things kind of straight in my head, so in terms of organization, I'm going to plug in all the traumatic events first and then the stressful but non-traumatic events second. So I'm going to go motor vehicle accident, combat, assault, and disaster. Okay? And then I'm going to put in infidelity, illness, work relocation, and financial collapse. Okay? Did I have to put them in that order? No, it doesn't matter. I can put them in all over the place. But if I put them in like some sort of general thing that makes sense to me, I can at least kind of see when I graph this out kind of where things are at, trying to look for different patterns, so on and so forth. So I'm going to go through and go to plots. We'll just put vignette on a horizontal line, just so SPSS is a terrible plotting program, but at least it'll give you kind of a general sense of what's happening. And then options, we'll ask for vignettes, descriptives, estimates of effect size. We won't ask for homogeneity variance because we already know what it's going to give us there. Hit continue. And then hit paste. And again, I'm going to end up with something that looks about the same as what I had before. I just got a lot more repeated assessments on this. Okay. I'm going to go through highlight and run this. Okay. So here, want to go through and look at my within subject factors, making sure that I've entered my whatever within subject factors I think I'm entering here. That's looking okay. All right. John, what are you, look at that descriptives table, what are you seeing here? Yeah, I mean, these means are looking pretty much the same. Everything's looking pretty much identical, right? Which doesn't make me super hopeful for things, okay? But I've got a large sample. Like, this is a very, very large sample that I've collected, so take some solace in that. Going to ignore my multivariate test. We're going to ignore my sphericity test, right? And again, it's violated, but we assume that it is anyway. But Nick, what are we seeing on my test of within subjects effects?
You do have something.
Yeah, I got it. Pretty easily achieved a reliable, effective mind within subject treatment, right? And Evelina, tell me what this means. So I've got a significant within subject effect for vignette. What does that mean?
We're observing variability across the different outcomes by vignette.
Yeah, exactly. All this is saying is that the average score across these different repeated assessments, they're not all the same. Like, we have sufficient evidence to claim that there's some reliable differences somewhere in there. We don't know where, but we've rejected the null hypothesis that the mean score across all of our repeated measures is identical. Now I'm interested, right? Because as John pointed out, my mean scores all look pretty much the same. But with a sample of this size, I've got clear evidence of reliable difference. Hypothesis language. These data are saying that these data are unlikely, assuming that the population means, or the populations from which each one of these assessments are pulled is all identical, right? So this is good. This sort of gives me hope, right? That's the whole reason I ran a repeated measures design on this, because I didn't want to have 300 people for every single vignette I wanted to calculate. So it looks like the differences are probably very subtle, but we are seeing systematic differences across groups, or across assessments. So here, again, this is my within subjects effects. This is all looking out over here. For our one-way ANOVA, this is basically all we're worried about, right? This is just us pulling out individual differences to reduce my error term. My error term for my repeated measures, again, is going to be down here for my greenhouse geyser. The one way, they're all the same, but as we move forward, that's what we're going to be looking at. Again, ignore within subjects contrast for right now. Test of between subjects effects. This is my between subjects. This is my error term that we're getting off in this corner here. And then if we take a look at once again, these are marginal means that are going to be the same as your observed means. John, you said there wasn't much difference in terms of my means. I'm seeing all sorts of differences here. What's going on?
Looks like the scale they used is pretty small.
Yeah, it's just basically did a hyper zoom, right? This is everything in my vertical axis is less than 1 point on a 0 to 8 scale. So it's just hyper zoomed in on this, right? Another reason why you should never try and present anything that SPSS is giving you, because that's going to be useless. But it does look like, in general, remember that what I did is I went through and I plugged in my the four vignettes related to trauma first, and then 4 vignettes related to other stressful but non-traumatic events second, right? I don't know, this is where we're going to go next, but I could start to maybe have hypotheses about differences in people's willingness to provide friendship to traumatic or non-traumatic events, although in my trauma, anybody remember what we put down here? Combat, right? That's interesting, right? So we've got car accident, sexual assault, and disaster. That's combat, right? It's not a big difference, but it's clearly not the same as these other guys, right? And then so our non-trauma stuff, we've got kind of all over the place, right? But it looks like at least within these data, we've gotten enough to say, all right, it looks like there are maybe subtle differences in how people are responding to this, which makes me happy, because really I'm asking people a loaded question here. Right? How willing are you to provide friendship to people? That's a no cost. You just say 8s across the board, right? But even here, when we're asking people for a hypothetical, we're still seeing some difference, right? So that might help me sort of maybe make a stronger interpretation, even though effect sizes are going to be pretty subtle here. Okay. All right, questions about running our basic one-way repeated measure ANOVA in terms of getting our omnibus stuff. People feeling okay with this? Okay, cool. So let's go through. So we've got our our omnibus tests. But that's not going to be where we want to stop with this, right? We want to go through and probably, hopefully, have some specific ideas about what's going to be going on with this stuff, right? So in terms of effect size, I'm going to go through, have a screencast video I'll refer you to on going through and calculating effect sizes for your repeated measures designs, just to save some time so we can make progress in here. But options are your eta squared, just like in your between subjects ANOVAs. This is going to be a proportion of your total variance attributable to effect. So we could say with our eta squared, X proportion of the variability in our outcome is attributable to our repeated measure. Problematic though, in that, as we talked about before, your eta squared is sensitive to the number of factors that you have in your design. Okay, so let's say we've got a 2x2 ANOVA, right? And you'll have here you have a sum of squares effect for A, for B, and the A times B interaction. Eta squared is going to take that total. It's all this variability that's not attributable to your effect. It's going to dump it in the denominator, even though you've got, these other effects. So if I'm looking at the eta squared for effect A in this factor, right? It's going to be the sum of squares, the variability attributable to the sum of squares for factor A over all the variability in the data, right? Well, you make an argument that doesn't seem fair because we'll have had systematic variability accounted for by factor B in the A by B interaction. That's not error. So do we put that all on the bottom, right? So we've got some problems here. And what ends up happening is we got probably eta squared is an underestimation of the magnitude of effect, and it's also not going to be comparable across different designs that have different factors. The more factors I have in there, the smaller, particularly if factor A, B, and sort of all those interactions are correlated with one another, the unique variability attributable to those is going to get smaller and smaller, and so we've got some problems. Eta squared is nice in that it's easy to interpret, right? But problematic because of it's probably going to be pretty small, and it's probably not going to be comparable across designs if the or comparable across projects if they have different designs. Other option is partial eta squared, right? It provides an index of sort of how much variability within the context of unexplained variance. Okay, so of all the stuff that's not attributable to factor A and the A by times B interaction, what proportion of the remaining variability is attributable to factor A? So partial eta squared is going to be the sum of squares effect over the sum of squares effect plus an error. Basically what this is doing is capitalizing on the fact that there are other things in there acting as controls. If it's accounted for, we're not worrying about it. We'll chalk that up somewhere else, right? But the problem with partial eta squared for repeated measure design is that this model contains multiple different error sources, right? So I've got sum of squares, and if you look into how SPSS is counting eta squared, they're just looking at this stuff. And we've got all of this business over here that's not being included in my partial eta squared calculation. And so for a repeated measure design, if I'm comparing my partial eta squared to, from a repeated measures design to a between subjects design, I'm going to have my denominator, my partial eta squared is going to be a whole lot bigger for my between subjects than in my within subjects, because in my within subjects, we've conveniently just partialed that out and are not considering it anywhere, okay? So the solution for calculating effect size, an omnibus effect for your repeated measures ANOVA is going to be something we're going to call generalized eta squared, okay? Generalized eta squared is what we're going to do is we're going to go through and we're just going to incorporate all portions of unexplained error in the calculation of our statistic, okay? You can get generalized eta squared from parameters provided in SPSS, but The specific calculation of generalized eta squared is going to depend on your study design and what effect that you're going through and taking a look at. Okay. So for our one-way design, it's going to be pretty straightforward. For generalized eta squared for a one-way repeated measures ANOVA, you're going to have your sum of squares for your repeated measures factor, right? So either vignette or time in our two examples. We're going to take that over the top of sum of squares from your repeated measure, sum of squares from your between, and your sum of squares from your error term, which is your repeated measure. And so now what we've done is we've taken all of that variability and then gone through to calculate generalized eta squared for the one-way design. Now, in most cases, your generalized eta squared will be larger than your eta squared, and your partial eta squared will be bigger than your generalized eta squared. Emilio, is this non-equivalency going to hold for our one-way designs?
Or just the one way, not for repeated measure?
Yeah, right. Why is that?
Because for the G, we have the between subs.
What's that?
I mean, for the eta, the generalized eta squared, you'll have the between subs.
Yeah. So what's going to be the relation between generalized eta squared and eta squared for your one-way design? Yeah, they're going to be the same, right? Because in your for a one-way ANOVA or a one-way repeater measure, this is the total variable. This is all the pieces of the parts that you have there, right? So for a one-way design, your eta squared is going to be equal to your generalized eta squared, and then your partial eta squared is going to be bigger because we're going to pull out this big between subject factor that we're not even taking care of, or we're not even considering, right? But as we start to get into mixed factorial designs and things like that, we'll typically see this because other sums of squares that are attributable to other between or within subjects factors, systematic stuff isn't going to be included in here. So you're going to see your generalized eta squared be larger than your eta squared, but your partial eta squared always going to be larger because it's not accounting for that all the individual difference variability is getting chunked out of there. Yeah.
Yeah, for the partial eta square, SS effect over SS effect.
What's that?
For the just the partial eta square, the two SS effects, are they different effects, or we're not just combining one?
Nope. Yep, this is just, so again, for the partial eta squared, remember you're saying, and we'll get into this sort of later on when we start adding in other predictors, you're saying of the total variability that's not attributable to other factors, how much can we place on this factor, right? So if this is factor A, right? So you take the sum squared of factor A over the sum squared of factor A plus the error, right? So if I take my total variability and I pull out variability that's attributable to factor B and factor C, what do I have left? Variability that's due to error and factor A, right? So yeah, this is going to be the same number, and this is just going to be your error term. And I'll walk you through examples in that screencast video. It's not super long. We'll just go through and we'll work through the examples that are provided, show you where to go through and calculate stuff. It should be pretty quick and straightforward. So those are, so again, if you take a look here, right, this is sort of basic calculations. So you take sum squares within, over the top of sum squares within, with sum squares between, so sum squares error. This is going to be your generalized eta squared for the first one. Same thing for this second example. Sum squares for your repeated measure over sum squares for your repeated measure plus your between plus your within, right? Pretty simple, straightforward stuff. For the one-way design, what starts to get tricky is when you start getting into factorial designs and whether or not you're measuring observed or manipulated factors. I've got an article that I'll have you guys jump into and go through and create another calculator for different effects and things like that. Questions here? All right. So we've done our omnibus tests. We've gone through and we've got our omnibus effects. Now we need to figure out how we're going to go through and start making interpretations based on that. Okay. Like we talked about before at the end of last semester, just because we've got our omnibus effect, we then need to go through and do something with it, right? It's just saying, hey, the means across my repeated measures are different. It's probably not going to be sufficient for anybody. What starts to get complicated for our repeated measures designs is that we have additional model assumptions that we need to take into consideration. And for mixed designs, we have the possibility of both between and within subjects factors. We need to handle it a little bit differently, so things start to get complicated. You want to have a game plan before you jump into the middle of this stuff, because if you just look at all possible pairwise stuff across, it'll be a mess, and then you'll be able to interpret it all, it'll be way too much, okay? So, common procedures for looking at specific effects. Trend analyses, we're talking about this, is going to be for cases where the ordering of your assessments makes some sense. Linear contrast and planned comparisons, and some obvious or some exploratory post hoc testing. How you develop your approach is going to depend on your specific hypotheses, right? Why did we do the study in the first place? Hopefully you have a reason for why you did the study in the first place. That'll help you a great deal. Conceptual considerations, which effects are potentially important, which ones are maybe not so important. The design of your study, how you've gone through, put things together, and the type of effects that you observed, and things along those lines. All of these things need to go into your decision on how you're going to go calculate these effects, how you're going to approach different stuff. So review from last semester. A couple things we need to be thinking about in terms of developing a strategy. Want to be thinking about our per comparison error rate, right? This is the probability of our type 1 error for any given test. This is just our alpha level, right? So this is saying, for this specific test, this is the likelihood I'm willing to make of making a type 1 error, where I'm saying that there is an effect when there's in the population when there's actually not. This being different than your family-wise error, right? Family-wise error being the probability of committing at least one type 1 error across a series of comparisons, okay? Again, we're calculating this is 1 minus your alpha level to the C power, this being the number of comparisons that you're making, right? So for 4 comparisons at alpha equal 0.05, the likelihood of me making at least one type 1 error within that set of 4 comparisons isn't 0.05 for each one of those. The likelihood of me making a type 1 error at least somewhere in that, at least one in that set of comparisons is much higher, right? And so this is our consideration. These are our concerns that we're just capitalizing on random chance. And as the more comparisons that we run, the higher the probability of making a mistake is. All this starts to become concerning if we're working with designs with both within and between factors and a lot of repeat measures, and everything's crossed with everything else. About a million different ways to look at stuff, and if I look at them all, I'm going to make a lot of different, I'm going to find a lot of interesting things that I can't explain that are probably just random hiccups in my data. Okay, so my family-wise error bounded between. That's not view, that's your family-wise error. By your somewhere between your alpha level and C times your alpha level, right? This is a correction you make for Bonferroni, right? Your family-wise error rate is going to be somewhere in between there, but it's generally going to be pretty close to just the number of comparisons times your alpha rate. Okay. So for our follow-up tests, wanting to be selective, right? We're wanting to select tests that are meaningful, things that are going to tell us something. Things that, if I'm going to spend a hypothesis test on it, I want it to be something that's worth spending a hypothesis test on. Again, as we talked about before, all possible comparisons probably not meaningful or interesting. You're wasting power if you're going to correct for all of them. And now all of a sudden I've got 15 different tests to account for instead of the 3 I'm actually interested in, and have fun with that discussion, because who knows what's going to happen there, right? Again, wanting to go through and choosing a strategy that does a reasonable job of sort of compartmentalizing these things. SPSS isn't going to do it for you. SPSS is just going to run everything at per comparison error rates, unless you do post hoc stuff, and then you post hoc things for tests that you can't interpret anyway, right? So you want to go through and make sure that you have a game plan ahead of time. Again, wanting to have a good reason for examining the things that you're examining. And this comes through good prep on the front end, right? But where we run into problems is we just say, hey, I wonder if X is related to Y and cross with X in terms of moderation of something. I don't know, I could get some stuff, but what do you expect will happen? I don't know, I just want to see if things turn out. There's a time and a place for that stuff, and that's fine, but if you're going to go through and report something, and put something together for a publication or a thesis or something along those lines, now all of a sudden I'm stuck in a reason where like maybe X does change the nature of the relationship between Y and Z, and I find an effect, but now I have to explain it, and that's real hard, because I don't know why that should, or I sort of have only speculating. It starts to get tricky. If you say at the front end, based on what I know about this area, this is what I think should happen. These are the things that are important. These are the things that I could test. This is the stuff that I want to test based on my research question. You're going to be on strong footing. Now you're going to get reviewers who are going to say, oh, why don't you test all possible everything's. You say, well, cool, I gave you enough means and standard deviations. You can do that on your own time if you like. That's not the point of the study. The point of the study is this, and that's why we're doing stuff, right? You're on the theoretical high ground in that situation. Okay? So, thinking about our a priori tests versus our post hoc tests. If we're talking about our a priori comparisons, remember that we're thinking about these. This is a small set of theoretically meaning comparisons that you've decided on before you even collect the data. Before you even run one participant, you're saying, these are the tests that I'm going to do. Because what we're doing, typically looking at these with a set of linear contrast, independent sample t-tests, and what we typically do, tradition is to look at these for comparison error rates. You're calling your shot. Before you even collect data, before you even sniffed up a data set to run through SPSS or any other such thing, you're saying, these are the comparisons, and this is how I expect them to turn out, right? If you do that, you're within your right to look at those per comparison error rates. Now, some people will make an argument, Hal will make a little bit of an argument for this, or for going through and using like a Bonferroni or a density correction, even just to be super careful. But the alternative is also that, from a theoretical standpoint, if we're aligning ourselves with Paul Meal, is there such a thing as a type 1 error? No. It's not everything. Nothing's going to be exactly identical, right? And so we've got to put a lot of worry into identifying. So the worst thing we can do is we can identify direction, an effect that's in the wrong direction, right? Like I can say is A is bigger than B when actually B is bigger than A, because they're never going to be exactly identical, right? Sometimes what people will do is you go nuts in terms of start correcting everything, and then that's problematic because our analyses are almost always underpowered, right? We're starting taking our behind where everybody else is starting, and then kicking ourselves another 15 back because now all of a sudden we've put this giant cap. Oftentimes, if you see people saying, oh, I Bonferroni corrected a billion different things, it's probably because they already went through and looked at it and found that everything they wanted to interpret met the threshold, and then Bonferroni corrected to be sort of conservative, you know. Or they don't know what they're doing. They say, well, I Bonferroni corrected everything, and now nothing's statistically significant. Again, not appropriate use. Bonferroni is and Dunsetting. These aren't post hoc comparison tests. These are corrections that you can apply if you choose for a small set of planned comparisons, not to be Bonferroni corrected for everything. Okay? John, I think that paper at Patrick's that you were working on, I think they wanted like to Bonferroni correct like 16 different tests or something like that. We had to help craft a response on why that was a stupid idea, right? But sometimes you'll get that, you want to be able to communicate why, oh, you're not going to do that, okay? So this is our a priori comparisons. Our post hoc comparisons, generally what this is going to involve is an analysis of all pairwise, okay, or all interpretable pairwise comparisons. And typically these are ideas that we develop after we've taken a look at the means, right? Conveniently, after we've looked at the means, I've decided that these two are really the ones that are super important to take a look at. The idea is that from a theory-based standpoint, the moment that you look at those means, you already ran all possible pairwise comparisons in your head. Not statistically, but you've already done it. And so we need to go through and we need to correct appropriately for us just cherry picking the most extreme values and deciding for whatever ad hoc reason that we've decided that those are really the most important things to be taking a look at, okay? post hoc procedures provide a correction for family-wise error. SPSS will give you post hoc tests all day long. The problem is the way they're doing it is probably correcting for things you can't make a reasonable interpretation of anyway, so you always want to make sure that you're being careful, even when you jump into post hoc comparisons, that you're getting the right correction, because otherwise what it'll do is it'll overcorrect for stuff that you can't interpret anyway, and so then it doesn't make sense to correct for that, because that's an apples and oranges comparison. Okay. And again, always remember that the limited set of planned a priori comparisons, this is going to be the most theoretically, methodologically defensible approach. Now, it's not to say, and for you experimental folks, right, you're more often tasked with reviewers saying, well, how do you rule out X, Y, and Z, or how do you know it's not this versus that, or the other things, right? Now, there may be things that come up after you've run your analyses that you can say, well, I should probably run this just to make sure to try and rule out X, Y, and Z. Sometimes those things happen as you're developing and trying to interpret, but in general, if you can say, this is the set of comparisons, this is the reason that I'm doing this test, this is the reason the whole study went down in the first place, is to test these specific things. And there are other things that might be kind of interesting to kind of poke around and explore. Those are exploratory tests. I'm going to go correct for these ones. But these ones are the reason that we're doing the study in the first place. This is what I think is going to happen. And so you're sort of laying things out before I get started, before you start mucking around and looking at other stuff. If you want to report all possible pairwise comparisons, you need to have a really strong rationale for doing that, because otherwise it looks like you're just poking around in the dark and providing ad hoc justifications for what something may or may not be down the road. I'll review people sort of coming back to people sort of thinking about this. Okay. All right. So if we're going to do specific tests for repeated measure ANOVA designs, if I have ordered means, one way I can do this, and this is often something that is going to be advantageous, it's not necessarily the individual comparisons, it's the overall pattern that's it's the more interesting piece of things, right? So, for example, in our ordered means example, right, we were looking at depression scores at intake, 2 weeks, 4 weeks, and 6 weeks, right? Whether or not there's a difference between symptoms at 2 and 4 weeks is probably not terribly important, right? What I might be more interested in this situation is testing to whether see the overall trend of means over the course of time, right? And if that's important, this is where we might start looking at trend analyses, okay? Trend analysis is going to give you a test of the shape of the repeated measure. It's going to, your observed effects in your trend analyses, it's going to be determined by the order of means and the magnitude of the differences in your means. This is what's going to contribute to that effect, right? If I go through and I run a trend analysis on the ordered means that we ran, that's going to mean something, right? Because I've got baseline 2, 4, and 6, right? But if I scramble those up, it's going to change my trend analyses because I've changed the order of the means around into something that doesn't make any sense, right? Generally, when we're looking at trend analyses, we're looking at linear and quadratic types of effects, but what SPSS is going to do is it's going to give you polynomials up to however 1 minus the number of points that you have in your repeated measures, okay? And so what you're going to start to get is you're going to get cubic trends and fourth order polynomials and fifth order polynomials and so on and so forth. And some of those effects might even be statistically significant, right? If you want to interpret those, you better have a reason why you specifically think that this pattern of means is going to follow a quadratic trend or a cubic trend or a fourth order polynomial. I challenge you to find me something that you're going to do that you predict on the front end of fourth order polynomial stuff, right? So again, don't get tricked by just saying, oh, that's a p-value, I'm going to go through and I'm going to interpret that. Stick with parsimony here, unless you have a strong theoretical reason for why means should do this over time. Probably the cubics and the quadratics are probably be what you want to focus on, okay? So Trend analysis is identical to plan comparisons, right? So we could do these by hand if we wanted to. I won't make you do these by hand. We'll just go ahead and let the SPSS do this for you. They're basically, SPSS is just setting a series of weights over time that are consistent with whatever linear, quadratic, whatever polynomial trend is going on. If you're thinking about running a trend analysis in your data, if you've got ordered means, you want them to work. This is going to be best if you have sort of order the same equally spaced assessments, right? So in our example, we have baseline 2 weeks, 4 weeks, 6 weeks. That makes some sense, right? Everything's kind of even Steven. If I want to apply a trend analysis to, I took baseline and then 1 week and then 1 week and then a month and then 6 months, that's probably not going to fly. I mean, because what you're assuming, what your trend analysis is going to assume is that you have equally spaced assessments. It's going to treat these two as if, or these ones as if they're all equally spaced, and that can start to throw off interpretations and things along those lines. So you want to be careful with that. Questions about trend analyses? All right. If I have unordered means, this is going to limit our trend analysis. If our repeated measure doesn't have any meaningful order, right? Like our vignette study, you can't really run a trend analysis because the trend analysis is dependent on some sort of meaningful sequence of events, and that's not, it's just counterbalance. So trend analyses, SPSS is going to give me one, but I shouldn't interpret it because there's nothing to interpret there. Or if my repeated measure has some sort of natural order, but I'm not expecting it to follow some conventional polynomial pattern, right? I'm expecting things to kind of do this and then kind of continue up or something. That's not something that actually follows a smooth curve, right? And so then, sort of the extent of, I mean, again, SPSS is always going to give me that, and it's going to test it, but whether or not I can interpret it is a completely different question, right? And so if I don't have any meaningful order, if I do, but I'm not expecting it to follow some sort of set trend, what we've got is we can then fall back on our within subjects plan contrast paired sample t-tests as going through and taking a look at stuff. Okay, so a review of our plan contrasts. Nice thing about our contrast is this allows us to go through and take a look at differences between means or sets of means. Okay, this is just a generalization of the t-test. It's just giving us a more flexible way to go through and look at things. Okay, so for example, when we get to our unordered means, I've got 8 different vignettes, right? And I don't know if I want to look at all possible pairwise comparisons between those vignettes because that gets kind of tricky. What might I do that might be an interesting way to go through and see what's going on in that set?
Rate the trauma against the non-trauma.
That's what I think, right? So I've got 4 vignettes that are trauma, 4 vignettes that are stress but not trauma. I might be interested to see whether or not people on average are rating higher willingness to provide friendship for people who experience traumatic events versus non-traumatic events, right? I can't do that with a t-test, but I can do that with a contrast if I set it up correctly. So these are the types of things that we can start doing. We also saw that, and this is a post hoc thing, right? But I saw that among our trauma sample, who do people seem less likely to want to provide support to? Combat, right? I can set up a contrast to see whether or not people on average are less willing to provide support for a combat versus the combination of those other 3 traumas together, right? Now that's not something I planned ahead of time, but I can certainly use a contrast to do that and then provide corrections for sort of exploratory tests and things along those lines, okay? So remember, contrast is just going to be a specific specification. We're just going to specify linear combination of means, weight of x1 plus weight of x2 plus weight of x3. So again, value of our contrast is going to be the sum of our weights times our means for each assessment point. All that we're saying is that this is just a linear combination of weight of sum of the weighted means. If everything is 1, that's just the sum of the means is going to be the grand mean in this case. If we take set our weights, all of our weights to 1 divided by the number of assessment points, it's just going to be the mean of all group means, right? If we're talking about linear contrasts, we want the sum of our weights to be equal to 0. These are going to be the types of contrasts that are going to be effective and useful for us. So we've got 3 means, 1, 2, and 3. If I weight A1, 1, A2, -1, and A3, 0. What are we testing here, Leila?
Sorry, can you repeat the question?
Okay, so I set for my weight for X1 is 1, my weight for X2 is -1, and my weight for X3 is 0. If I add 1 and -1 with 0, some of my weights is 0, I've got a linear contrast. What am I testing functionally here? What am I comparing? The means of which groups? Which ones are probably going to be compared directly within this? What means am I comparing if I write this out? Anybody up or out? 1 and 2, right? Takes mean 1 against mean 2, right? Because 0, weight, 3's gone. So this is just a t-test, right? Essentially, this is just saying, what's the difference between mean 1 and mean 2 here, right? So looking at just the difference between my two groups. Same thing, alternatively, if I said A1 to 1/2, A2 to 1/2, and A3 to -1, I sum these weights, they sum to 0. Laura, what's my comparison here?
You're comparing A3 to A1 and A2?
Yep. I'm seeing if there's a difference between the combination of A1 and A2, or excuse me, X1 and X2 with X3. So if we go through 1/2, 1/2 in my weight, again, is there a difference in group 3 across the average 1 and 2? So remember that for these contrasts, how we select our coefficients, identify which sets of comparisons we want to take a look at. We assign rates as the reciprocal of the number of treatments within the set, and then we assign as one of the sets to be negative. Nick, which one are we usually set to be negative? Do you remember? Okay, so but yeah, so we've got which anybody remember how we determine? And at the end of the day, it's arbitrary, right? But just in terms of making sure that things are interpreted in the right direction. Haley, you know?
Isn't it just which group you think will have less of something?
Yeah, the group that I think is going to be less, right? That way, my test ends up being, or the value of my contrast ends up having the same sign as kind of what I expect. Right? If I switch it around, then the group with the larger is going to be a negative, and so just in terms of thinking about it as you're writing this out to make sure everything plans up together. So again, if I've got 5 means, X1 to X5, and I want to contrast X2, the first 2 against the last 3, right? We say X1, X2, X3, 4, and 5. So we've got 2 means here in this group, 3 means in this other group. We say, all right, well, 1 divided by 2, 1 divided by 2, 1/3, 1/3, 1/3. I expect these 2 to be larger than the average of these 3. Assign those to be negative. Everything lines up. Those are my contrasts. Right? So the sum of my linear combination here is essentially 1/2 times X1 plus X2 minus 1/3 times X3, 4, and 5. Okay. If we set our coefficients so that the absolute value sums to 2, this is our standard set. Remember, this is helpful when we're going through and we're calculating effect sizes. If we set a standard set, it means that the value of our contrast is actually in the scale of sort of whatever our measure is. So I could set this I could set my values here to 3 and 3 and 2 and 2 and 2, right? So if I take 3 and 3 is 6, and I subtract 2 and 2 and 2, that's 6. I've still got a linear contrast, right? But what I don't have is a standard set, because if I add 2 and 2, or 3 and 3, and 2 and 2 and 2, if I'm taking the absolute value of that, I end up with a total of not 2, I end up with a total of 12, right? So that's, this, if I did that, that'll still give me the right test if I run it correctly. What it won't do is I can't use the value of that contrast as the numerator of my effect size, right? So again, wanting to note that in general, if we have wildly different cell sizes, this is going to compromise the calculation of our trends. But what's nice in our one-way ANOVA is that we have the same number of people in each cell, because it's a repeated measure design. It's the same people across time. So linear contrast in our repeated measures ANOVA. Value of our contrast is going to be the sum of our weighted means. And our t-test is going to be the value of our contrast over the sum of our squared weights times our mean squared error over the number of people that we have in our sample. And this mean squared error is taken from our ANOVA table. It's going to be this error term right here that we're pulling from. It's going to be that repeated measures error term. And then we're going to test this against a critical t with degrees of freedom taken from our ANOVA table as well. Okay. We just tweak this a little bit to make sure that we're running a correct test for our within subjects effects. Okay. If all we're interested in is simple pairwise comparisons, we can also fall back on paired sample t-tests. Okay. Problem with that is particularly if I have 3 repeated assessments, right? I've got 3 different pairwise comparisons I can make. If I've got 4, then that starts to get bigger. If I got 5, right? If we just want to go through and test all possible mean time points with all other possible time points, one, a lot of those probably aren't going to be theoretically interesting for some reason, and then we're just all of a sudden starting to rack up a lot of tests. Okay, but if you've got a number of, even if you have a number of planned comparisons, right, that you called your shot. This happens sometimes. I have 14 planned comparisons. You can't have 14 planned comparisons. You still need, if you're starting to get sort of a lot of stuff, you need to still probably go through and think about how to go through and compare that stuff. Okay. All right. Thinking about the problem with, as we talked about before, some traditional methods of going through and testing running our contrasts and things along these lines. If you get into sort of the nuts and bolts of some experimental design, a lot of this is built on pulling error terms from your overall ANOVA table. The problem with it, as we talked about last semester, is all these tests are predicated on the assumption that you haven't violated assumptions, that everything's randomized, that you have equal cell sizes, that you haven't violated homogeneity of variance types of things. And if you do violate those things, all of a sudden we start to lose confidence that our tests are good tests of what we're trying to do, right? And as we start to increase the complexity of our designs, adding in between and within subjects factors, all of a sudden we start to become more and more concerned about whether or not these tests using the classic approach, where I just go through and I pull error terms from my overall ANOVA table, whether or not that's going to be viable, okay? And so if you've got a situation where you're not sure whether or not you've met all of the assumptions, or you have violations, or you just got weirdness in your data, and what you're looking at is some paired comparisons between some stuff, particularly for your repeated measures designs. If you've got a lot of people, these are, again, incredibly powerful tests. You lose some power by just running and falling back on paired sample t-tests, but you're going to have greater confidence that if you're detecting effects, that those are actual, real, true effects that are all following the same assumptions that you had before, right? And so our one-way ANOVA, or one-way repeated measures ANOVAs are nice in this regard, in that you don't have to worry about cell size, because cell size is all the same, right? If you're measuring the same people over the same period of time, or the same group of people over multiple assessments, oftentimes variability in your assessments are going to be pretty comparable because you got the same people going through. Not always, right? I'm likely, again, for clinical folks, if I measure people, variability of, say, clinical symptoms at baseline versus clinical symptoms at post-treatment, where am I going to see more variability? Where we start or where we end? When we start, you're going to see some variability, right? But when we start, everybody's upset and needing treatment. What about when we end? What's happening there? What do you think, Kate?
It could be, it depends on the person.
Yeah, it depends on the person, right? So sometimes we get people who are doing better. Sometimes we have people who are stayed the same. Sometimes we got people who might have gotten worse over the course of that time period. So in clinical stuff and treatment stuff, we often find that looking at like the standard deviation of the difference score or the standard deviation of the pooled standard deviation is often considerably larger than the standard deviation of people at the first time point, right? But these are all things that we want to be thinking about as we're moving forward and thinking about how we're calculating our tests and our comparisons. Okay. So we'll pick up next time, jump into post hoc stuff. Thinking about this next set. So we got our first set that's due